Okay, thank you very much. Sorry for the delay. Yeah, so this is a project we've been working on at the VU. I just moved to London, so that's why there's two universities on there, and my name badge doesn't say where I'm from, but yeah, hopefully that's not too confusing. So we've been doing some sort of formalized mathematics again. This is the formalized mathematics session, and we've been doing some mathematics in the field of number theory. So actually, of the four of us there, three of us are sort of professional number theorists. And Baanen is a PhD student really in formalization. So quite a mixed group, but all of us are very interested in formalization, and we hope to well, continue doing things in this field. So okay, let's go. So this project is about sort of well, formalization in number theory. And if you look on the left-hand side, I've tried to visualize the sort of problem that number theorists like. So we start with a 2 by 2 by 2 cube, right? So there's 8 little cubes. And if you rearrange them, you find you can almost form a square, except there's one point missing. Okay, so this is the sort of thing number theorists like. It's about the integers and sort of multiplying integers and adding integers and sort of what sort of different combinations you can make. So this is saying that 2 cubed plus 1 is 3 squared. Okay, and we like these sort of problems, and we'd like to try and generalize these sort of problems to sort of more and more extreme cases. That's a whole research topic in itself. And well, it's a bit hard to see on the right-hand side what's going on because there are so many cubes involved. But I'll tell you what's happening. What's happening there is we're trying to solve the equation a square is a cube minus 13. So that little thing was a visualization of a cube of numbers where you take away 13 little cubes and you get a very large square of numbers. And so whether this thing has a solution or not is entirely non-obvious from looking at the equation. There's really no way to tell without trying a bunch of numbers and seeing what happens. So, well, this is sort of the main result of our formalization. We're really aiming to sort of build a toolkit that we can approach many other problems with, but this is sort of maybe, you could say, the hardest one that we managed so far with this equation y squared is x cubed minus 13. And it turns out it does have solutions. There are two solutions. I don't know if you can read it, but the answer is that x has to be 17 and y has to be plus or minus 70. So on the previous slide there, that was actually a 17 by 17 by 17 cube, which turned into a 70 by 70 square. Okay, so hopefully that makes the sort of problem we're looking at clear. They're very simple problems, which is why we like them. They've been studied for thousands of years. That's why they're named after Diophantine, who lived several thousand years ago. And they're still an active area of research. So it may look simple, but this equation here, x squared plus y cubed equals z to the fifth, is currently unresolved. No one knows how to show that this has no solutions other than x, y, z all equal to 0. Okay, so this is the sort of thing where Fermat's last theorem, is a sort of a part of this field. It's been resolved, but sort of many related things have not. And in general, this sort of problem of solving Diophantine equations is known to be undecidable. So there's no algorithm that can do this for us. And there's sort of a whole zoo of different things going on, right? All these different equations you can set up have slightly different techniques that you use. And well, one of my hopes personally is that formalization will maybe help us tame this zoo and organize it a bit better, because we sort of have a paper that comes out with a slightly new technique that's a variation on what's known, and they get sort of 3 more equations, and the sort of literature is sort of very unmanageable. And personally, I quite like the idea of some sort of formalized database of these things, but we're a long way from that yet. So what we did in this project is we formalized one technique, still quite an old technique, still not from this century, but from the previous. But it uses what are called number fields, which is sort of a second course in algebraic number theory topic. And we did it in 6,000 lines of code. I saw someone used LOI for lines of Isabelle. So we did LOL for lines of lean. We're using lean, but I'll try and keep this this a bit more general and just try and speak in a high level where possible. And so this is an XKCD about number theorists having no friends. So just leave that there. Okay. So what will I do in this talk? I'm going to try and focus on the general rather than the specific mathematics. I know that not everyone here is a number theorist or even cares. And I'll try and explain why these equations now that we've done are harder than the ones that people have formalized before. And this sort of thing has been considered before from a formalization perspective. And I'll also try and explain what makes this style of proof different from some of the more theoretical things that we've seen. Finally, I'll explain sort of 2 attempts at some automation that can make this sort of proof more convenient and lean, that hopefully might be of wider interest. We all need automation in our lives, right? So here are some sort of classic tools in number theory. So these are things which have been known for anywhere between 2,000 years and sort of 300 years. The first one is congruences, and this is an extension of the idea of some things are even and some things are odd, and an odd plus an odd makes an even, and it can't make an odd again. So this is a very basic tool, but it's very, very powerful. So this equation here, we can see can't have a solution because no matter what x and y are, as long as they're integers, the 2y squared will be even, the 4x cubed will be even, and the 13 is odd, so it just can't happen. So it's a very basic tool, but very powerful. I say it's due to Euler and Gauss because they sort of introduced notation for this, not because they really invented it. Descent is this thing that maybe you've seen where we proved that the square root of 2 is irrational by imagining that it's not, and that there exists an x and y that solve this equation, y squared is 2x squared. And then we make a smaller version by observing that y is even, therefore it's some 4y prime squared, divide through by the 2 and reach the same equation again with smaller numbers. So we get sort of by, whatever, the integers don't have a descending sequence, so we know that there can be no minimal non-zero solution. So this is also quite old, 400 years old. And there's quadratic reciprocity, which is maybe you haven't seen before, but it's still considered kind of a classic technique, I would say. And this sort of thing, I won't really explain this proof in detail, but it's about whether things are squares or not modular other numbers. And there's sort of a powerful theorem there, which lets you deduce kind of quite non-obvious properties about some things being squared mod other things and other things being squared mod other things. So these sort of tools have been used in formalization before. So notably, this goes back to sort of 2004 in Koch. So this is a classic equation also solved by Fermat, which says that for all primes p that are 1 mod 4, this equation, x squared plus y squared, has a solution. So 5 is 1 squared plus 2 squared, for example. So Terry formalized the resolution of this, and this sort of involves quadratic reciprocity. And well, it's quite nice, and it was done almost 20 years ago. We've also got some slightly more complicated looking things like the Fermat equation for exponent 4. So you might know this from Fermat's last theorem, x to the 4 plus y to the 4 is e to the 4. It is one case of that theorem that you can solve with sort of these classical elementary methods. Finally, in Isabelle, the 3 cases of Fermat's last theorem, some other related problems were kind of solved, and all these things use the sort of techniques I talked about on the previous slide. So these are what we call, maybe sort of classical techniques that you might learn about in a first or second course on the subject. So these are some really nice formalizations, and they're sort of done 15 or 20 years ago. So you might wonder, why are all these mathematicians trying to learn lean and then trying to do stuff which has been done already 15 or 20 years ago? And I want to try and convince you that what we did is a bit different and involves sort of some more techniques that require a lot more background material. And there's a reason it's taken sort of 15 years. Maybe no one else was interested, but maybe it's just a little bit harder. Okay, so why is this equation harder? This might be the most kind of mathematical slide of them all. So these equations where you've got 2 variables, you can think of them as a curve. You've got 2 variables, so when you plot the points where this thing is satisfied, you get a curve in the plane. And sort of as the degree of the curve increases, another related number called the genus increases. And so some of the sort of previous examples were things of genus 0, and some of them were things of genus 1. And generally, the bigger the genus, or the bigger the degree, the more complicated things are. So as soon as the genus is at least 1, we have a finite set of solutions, right, integral points on such a curve. And the curves we're looking at for this y squared x cubed minus 13, they do have genus 1. So we know the answer is going to be finite. But we would like still to list it, right? We like to solve these equations very explicitly, not just know that the answer is finite. So this is a plot of the curve here. And you can, maybe in tiny, you can see that there are some red points and some blue points. Maybe it's a little bit hard to see, but that's a blue point. That's the integral point, 1770. And these red points are rational points. So these are rational solutions to this equation that aren't integral. And that's one of the reasons why this sort of thing becomes hard. As soon as you've got all these rational points floating around, and infinitely many of them, then whenever you try and use something like congruences, the congruences kind of don't know the difference, right? So when you try and apply these sort of congruence techniques, you generally have quite a lot of points, modulo p for a prime p, and you can't really sort of get much control over it. You can't rule things out just by using congruences. And maybe it's kind of silly to say it, but the fact that there actually is a solution makes it maybe harder than if there was no solution at all. If there's no solution at all, sometimes that's just kind of easier to rule it out. So this is just to give you some idea why this takes a little bit more effort. But now I'm going to try and prove it for you. I'm going to be a little bit sketchy, so if there are any number theorists, I hope they'll forgive me for telling a few lies, but just to make it fit on the slide. The argument goes like this. You put the 13 on the left-hand side of the equation, and you factor a square minus something is, y plus the square root minus times by y minus the square root, and that thing is a cube. And then as long as you can check that the two things you factored it into are co-prime, maybe you can claim that each of those things are then a cube, right? If I've got a times b is a square in the integers, then actually a has to be a square and b has to be a square as well, as long as they're co-prime, right? If I've got. So if you could do that, you could then just kind of do a little bit of a calculation and say, okay, well, my y plus root negative 13 is a cube. Maybe there's some variables a and b, and then that means that some pretty long and horrible looking expression here is equal to y plus the square root of minus 13. And then you can kind of read off from that, well, the coefficient has to be 1, which means that b has to be plus or minus 1. And you kind of follow the logic forward. I won't spell it all out. But you reach this point, x is 17, y is plus or minus 17. So that's the crux of the kind of the argument. You have to do a few things, of course, to check this coprimality condition and to do all this algebra. But the big if here is, well, the if that I've tried to highlight, it is whether you can assume that the product of two coprime things being a cube implies that each of them is a cube, okay? And this holds in the integers, but unfortunately, in general, it doesn't hold in number theory, right? So we've added this square root of negative 13 here, and this kind of changes the behavior of this ring to make it behave a little bit differently than the integers do. And so this is kind of one of the key topics of number theory, is kind of understanding this failure of this sort of property. And so I'll just point out that even though I said maybe cubes should only factor into cubes, in this case, I mean, you can't really check it in your head, but I presented here to you two non-squares that when you multiply them together, you get a square in this slightly unusual ring. So yeah, I guess you have to trust me on that, but this kind of property does break, is the key point, and it can break, and here it breaks for squares, but hopefully not for cubes, otherwise this argument won't work. So the thing which controls whether or not this fails is known as the class group. And so this is a finite abelian group that you can associate to your field. So in this case, we've taken the rational numbers and we've added a square root of negative 13. That was the sort of setting which we made our argument in. And this has a finite abelian group associated to it called the class group, which has the property that, well, the thing we want to say that nth powers factor only into nth powers holds only when n is co-prime to the order of this class group. So if we can calculate this group and check that its order is co-prime to 3, then our argument succeeds. So the definition of this class group, I won't give it now, but it's been formalized previously by Baanen, Dahmen, Ashwini Narayanan, and Nuccio a couple of years ago. And this is where I want to kind of draw a bit of a contrast, maybe, between sort of general conceptual kind of proofs and sort of more specific and calculational proofs, right? So if we only wanted to prove that there were finitely many solutions, it might be enough to just give an arbitrary bound on the size of this group, and there we just need sort of finiteness. But if we really want to find these solutions, we really need to kind of calculate this group and get a very good bound on its size to show that it's not divisible by 3. Okay, so here I've kind of put these two things, right? When we're only proving finiteness, we can just kind of be lazy with any bounds and take them as big as we want. But when we're doing this sort of proof, we really need to be very, very tight with all the sort of bounds involved and make sure that we get kind of the smallest possible thing, because at the end of the day, when we're formalizing, it takes a lot longer maybe than if you're just computing things to really prove that certain things don't happen. So you want to make the bounds as small as possible so that your work in future is reduced. So how do we bound these class groups? Well, I haven't defined it for you, but I just want to give you a flavor of the sort of mathematics that's involved. So, well, what we actually do is compute these class groups rather than just bounding their size, which might be of independent interest. And we use this following theorem. I mean, it's a bit hard to read, so I will just explain it to you by sort of a sequence of pictures, okay? So these are some ovals, right? These are you take the lattice of all the integers, times the integers in the plane, and you take the function x squared plus 13y squared, right? And you put that oval around each of the integers, and then you rescale it until, so this is sort of, you take the same picture and you shrink it by a factor of 2, and you lay it over itself. And you need to keep doing that a number of times. So here we do it 1, 2, and 3 times. And it's, well, not easy to see from the picture, but it still doesn't cover the plane. But if you add it one more time, it covers the plane, okay? So what this theorem is saying is that if you find this number such that when you shrink this, these balls enough that they cover the entire plane, then that number is a bound for the generated zero class group, okay? So this is a sort of mathematics, even though it's quite algebraic, you reduce to a problem which is really quite, it's not linear because you have these x squared plus 13y squared, but really just sort of a real, semi-algebraic problem, I guess, would be the way to say it. And so we actually try and reduce this thing down to 1 dimensions and then have to bound some other functions, but we won't get into that. So even though it's an algebraic proof, the way you bound these class groups is actually you kind of embed everything into the reals and you work there. So that's a characteristic of the proof. As you may have guessed, when you calculate these class groups, you need to do a lot of kind of calculational things. So we want to kind of explicitly evaluate expressions like this in a ring like this. And this is sort of, you could do in several ways. Maybe you could try and get a simplifier, right? People in Lean, we've already heard, love to use the simplifier. But this is very inefficient. Once you get very high powers of whatever it is, your square root minus 13, kind of using the simplifier to kind of reduce them out all the time is not the best way to go. You could kind of set up a specialized ring or specialized type just for whatever you're doing, and then try and use extensionality and reduce the goals about the integers. This is what we did initially. But what we found was we wanted something more versatile. Well, we didn't need to make a new type, and we didn't need to rely on the simplifier being fast. So we introduced this tactic we called times table tac, which is basically rings like this. They have a finite basis. And in terms of that basis, the multiplication operation is just given by some matrix. And so we introduced a tactic which basically you teach it the multiplication table for a ring, and then it uses that multiplication table to do calculations. So at the bottom here, I've adjoined a square root of 2 and a square root of 3 to the integers, right? And I've computed this very long and complicated expression, which should be an integer for kind of symmetry reasons. And okay, you can't see it, but the next line is times table tac. And then it's done. So we kind of show that this can be used to compute quite complicated expressions fairly quickly. And it's more efficient than, say, using the simplifier in theory, but maybe not yet in practice. I guess, how long do I have left? Well, I'll say one last slide then. And that's, we also like to connect things to computer algebra systems. And we kind of prototyped a slightly extensible method for connecting to the computer algebra system Lean, which is a free and open source computer algebra system that, well, we set it up so that it connects either over the internet to a server that's publicly accessible that runs Sage. Sorry if I said Lean, I meant Sage, or Sage on the user's computer. And we tried to make a design that was kind of extensible by future users with relatively little effort. But yeah, I think I'm out of time, so I will stop there. Thank you.
Any questions?
Thank you for the talk.
So the study of number fields feels a bit weird to me because it talks about like equations between integers, which are first order objects, and somehow reals show up and other localizations of fields at whatever absolute values. And do you know if these are the only methods we know, or if we could do that only with I don't know, piano arithmetic?
What was the last thing you said? Last sentence?
If we could prove the same thing just using first order piano arithmetic.
Yeah, well, so first of all, yeah, you're right. Number fields are pretty weird. I guess that's why we like them. And number theory as a subject is kind of like a receiver. Like it takes from all the other mathematical areas and just uses whatever methods it can. I am not aware of any proof in that vein. I would guess no, but I don't know of a proof of that. I mean, it's certainly this, I think in this case, is the simplest proof known of solving this equation. It does definitely involve, yeah, doing a lot of stuff. So I guess I'm not qualified fully to answer the question. My inclination would be no.
Hi, that was really nice, and your pictures helped a lot. You focus on -13. Do your technique work for other numbers, and which other ones have you tried and succeeded for and failed for?
Yeah, so we did smaller numbers. I guess -13 was the biggest, and we had to do the most work, and kind of therefore it was the most interesting. It was also nice, like I said, to do an example where there actually was a non-trivial solution and kind of a non-obvious one. So we really kind of pushed for that. Basically, the elliptic curve is like the first one I think that's actually a rank one. So in that sense, we did the first one where we couldn't think of an easier way of doing it, or we couldn't think of a way of cheating. It absolutely should work. I mean, this last picture here in the bottom right, that's probably one of the bottlenecks, is kind of doing that sort of thing again. We have some better techniques for that, but we need to really compare this method with kind of existing class group bounds and kind of see, we need to kind of optimize everything if you want to do it at scale, basically, because at the moment it's a bit too case by case. But in general, this should work, you know, for a whole host of other